Good afternoon, everyone, and welcome you all for today's discussion. Today we are going to discuss about viscous laminar flow between two parallel fixed plates. And before starting to derive how various parameters, pressure difference, power required, and velocity distribution, shear stress distribution in flow between two parallel plates, we will discuss how pressure gradient is related to the shear stress gradient, because this is a very important relation that will be used in both laminar flow between two parallel plates and laminar flow through pipes and tubes. So we will first discuss what is a relation between pressure gradient and shear stress gradient. That is a cardinal relationship which will be applied in flow analysis of laminar flow between two parallel plates and flow through pipe. So let us start first discuss what is a pressure relationship between pressure gradient and relation between pressure gradient and shear stress gradient that I want to relate dp over dx equal to d tau over dy. This relationship we will derive, and that relationship will be useful for the other derivations. So this relationship, for deriving this equation, we will take a small element in a flow. In any flow field, we take very small element, three-dimensional small element, and we will discuss how pressure gradient is related with the shear stress gradient. So let us first define an element. This is a three-dimensional element A, B, C, and D. A dash, B dash, C dash, and D dash. And simultaneously, we have to define velocity distribution and shear stress distribution. This is a small element in a flow field, and dimension of this element is dx. This is direction z, this is direction y, and this is direction x. So if we want to define in two-dimensional x and y, we will take projection. We will take first we will take velocity distribution in two dimensions. This is the velocity distribution of flow field. This is because we know that velocity distribution, suppose from fixed plate to upper plate, velocity distribution is like parabola, and we will project here. We take projection here. In two-dimensional projection, you will find here point A dash, here point B dash, and we take projection here because this is upper surface, this is lower surface. So here point you will D dash, and here that is a C dash. And from this point to this point, you see that dimension here dimension is dy, and here dimension this is dimension dz, and suppose this is a pressure acting at this surface is P. So pressure that will act on surface B dash C dash will be equal to P plus del P over del X dx. This is a pressure, and here suppose on this surface shear stress is acting tau. So when we move up, shear stress will be here tau plus del tau over del y dy, because it is a function of y. Shear stress is a function of, because there is a difference in layer between two layers, between layer A, B dash, A dash, and between layer D, C dash, D dash. There is a difference of dy. So it is a function of del y. So what is it? Shear stress at upper surface will be tau plus del tau by del y dy, and same thing we can here represent. This is a tau plus del tau over del y dy, same, because it is always acting in conjugate, because upper layer just lower layer will oppose same shear stress. That is represented by this arrow, half arrow. Here it is a tau, because there is difference of dy between two layers, so the stress will be different. Due to this shear stress, shear force will act on the layer D, C, C dash, B dash, and due to tau, shear force will act layer A dash, B dash, B dash. So we have to find, because this flow is, we have considered the laminar flow, viscous flow, and under steady flow. Under steady flow, there is no force is acting, or a net force acting on this element will be zero under equilibrium condition and under steady, because when a steady flow there is no any acceleration. So here we have to find out under equilibrium condition what are forces acting due to pressure intensity of pressure is varying between surface A dash, D dash, and between surface B dash there is a difference of dx. So pressure is changing. Due to this pressure change, shear stress is also opposing the force due to pressure. So under equilibrium condition, there is no force acting. So pressure force due to change in intensity of pressure between two phases. So what is a pressure force? First is a pressure force. Pressure force equal to P into area. Area is a dy into dz minus P plus del P over del X dx into same area dy dz. So net force equal to, this will be eliminated, so net force will be equal to del P over del X dx dy dz. That is negative sign. You will find negative sign, that is equal to write it again, minus del P over del X dx dy and dz. This is a pressure force due to change in intensity of pressure in two phases, A dash, D dash D, and B dash, C dash C. Now what is shear stress? Due to shear stress, force will be applied. Due to this shear stress, force will be applied. So force due to shear stress. Force due to shear stress equal to tau plus del tau over del y and dy minus tau and whole multiplied by area. This area will be included, because this is area in which shear stress is acting. So area is equal to dx and dz. So this tau will be eliminated. So del tau over del y dx dy and dz. This is a force due to shear stress. Now under equilibrium condition, net force is equal to 0. Under equilibrium condition, so summing forces due to shear and due to pressure gradient. So summing these forces, so sigma fx equal to 0. So that is equal to minus del P over del X dx dy dz plus del tau over del y dx dy and dz equal to 0. So again, simplifying this one, we will get del P over del X dx dy dz equal to del tau over del y dx dy dz. Eliminating dx dy dz, so we will get del tau over del y equal to del P over del X, because these are independent variable. Tau depend upon y and pressure gradient depend upon X. Both are independent variables. So we can simply convert partial derivative into exact derivative. So we can write d tau over dy equal to del P over del X. This is equation number 1, and we taking from Newton's law of viscosity. Remember Newton's law of viscosity. What is Newton's law of viscosity? Tau equal to mu du over dy. So putting value of tau in equation number 1. So d upon dy mu del u over del y equal to dp over dx So we will get relationship mu d square u over dy square equal to dp over dx, or you can write d square u upon dy square equal to 1 upon mu dp over dx. So this is the relationship. These are two equations, equation number 1 and equation number 2. These equations we will use in derivation of the flow between two parallel plates. So this is a cardinal relationship we have to remember for further derivation of particular cases. So now we first discuss flow between two parallel plates. Flow between two parallel plates. So this equation we have to remember, that is a d square u over dy square equal to 1 upon mu dp over dx. This is the equation we have to remember. Now case that we are going to discuss, that is a flow, laminar flow between two parallel plates. So many situations you will find in engineering application that there are two parallel plates of infinite depth. Flow is occurring. So either case of parallel plates or case of the pipe through which in canal system we have seen that between two parallel plates flow is occurring. So that is going to discuss. So let us make a two parallel plates first. These are two parallel plates of appreciable length. Length is appreciable and thickness, width between these two parallel plates is a b, small b. This is small b. These are two parallel plates and flow is occurring between two plates. This is a flow is occurring between two plates. Some viscous flow is occurring between two parallel plates. So now we want to discuss here between two parallel plates there is a some distribution of velocity will be like this. This is a velocity, suppose this is a velocity distribution, because we know that in laminar flow, due to condition of flow separation, what are assumptions of this condition? That number one, these plates are appreciable length, and suppose this is direction x and this is direction y and this is direction z. So length of the plate is appreciable and this is y direction. Width of the plate is also significant, and this thickness along z direction, width is infinite. Width along z direction is infinite, means very large. This is the condition of the parallel, and here you will see if it is center line, and here velocity will be maximum, u maximum, and at any point here, suppose at distance y, thickness is dy. This is thickness dy, and velocity at this point is small u. If the velocity at this point is small u, as we move here up to b point, b by 2, velocity is maximum, and due to condition of no separation, flow along this surface will be zero. Velocity will be zero, and shear stress, as we see from here, that if velocity becomes zero here, the shear stress will be maximum. If velocity is zero here, shear stress is maximum. So what is the velocity distribution we have to find out? By using earlier equation that we have derived, that we are going to use this equation. So now reducing size here, if we defining of the problem, and we have to find out velocity distribution, we have to use this equation, d square u over dy square equal to 1 upon mu dp over dx. This was equation that we are going to apply here. And applying boundary condition, we will solve a general equation for velocity distribution between two parallel plates. So now integrating this equation with respect to y, first integration will give you du over dy. Everyone are familiar with this kind of integration. So first integration about y will give you 1 upon mu dp over dx y plus c1. This is equation number 2. Again integrating this equation with respect to y. So second integration will give u equal to 1 upon 2 mu dp over dx y square plus c1y plus c2. This is equation number 3. So there are two constants here in this equation number 3. So by applying boundary condition, now apply boundary condition. Apply boundary conditions. Apply boundary conditions. So first condition is at y equal to 0. Starting from here, at y equal to 0, u equal to 0. Putting here y equal to 0, u equal to 0 equal to 0 plus c2. So here from this we get c2 equal to 0. Constant c2 equal to 0. Now applying second condition, boundary condition. At y equal to b, again u equal to 0. When we reach from y equal to b, again you find that u equal to 0. When there is a flow is in touching with the surface of the plate, it becomes 0 because of the condition of no separation. So again putting here 0 equal to 1 upon 2 mu dp upon dx b square plus c1 b plus 0. Already c2 are 0. So here you get b c1 equal to minus b upon 2 mu dp upon dx. So putting values of c1 and c2 in general equation, we get velocity distribution from this equation. Putting these values, so you get u equal to 1 upon 2 mu dp upon dx y square plus, and putting value of c1 minus 1 upon 2 mu dp over dx into by. So taking common, what are common? 1 upon 2 mu dp by dx. So taking minus dp by dx. So 1 upon 2 mu minus dp by dx. We get by minus y square. This is a general equation of velocity distribution. This is equation number 4. Why we take minus dp by dx in bracket? That is a reason here. Because we know that pressure gradient along the flow direction is always negative. Because pressure P1 is always greater than P2. So P2 minus P1 is always negative. When we take dp by dx negative in brackets, this value inside the bracket is always positive. That's why we take minus dp by dx common and bracket. So this is a general equation of the velocity distribution, and from here we can find out to maximum velocity, what are condition of maximum velocity and what is the condition of maximum shear stress. So now let us take only final equation. So this is general equation that we will consider always. U equal to 1 upon 2 mu minus dp by dx by minus y square. By minus y square. This is general equation that we have derived. Now what are condition of maximum velocity? Where maximum velocity is occurring? So for maximum velocity we differentiate this because u is varying with y. So du over dy equal to 0 for maximum velocity. Now differentiating here 1 upon 2 mu minus dp by dx. This is a constant, that is you will find b minus 2y and equated 0. This is never 0 and only 0 can become b equal to 2y. So y equal to b by 2. At y equal to b by 2, from here at y equal to b, between mid, this is center line, velocity you see maximum. U maximum you will find at y equal to b by 2. So what is maximum velocity? U maximum equal to 1 upon 2 mu minus dp over dx and y equal to b by 2 by square by. That is a b square by 2 minus b square by 4. So that will be equal to we common take common. So 1 of b square upon 8 mu minus dp upon dx. This is a maximum velocity. This velocity is a b square upon 8 mu dp over dx. So now it is clear that maximum velocity. Now we have to find out where shear stress is maximum. For shear stress, already we can draw here. Distribution of shear stress will be like this. Distribution of shear stress will be like this. This is a shear stress distribution. This is a shear stress distribution. And we how this is a tau max at surface. That is a tau max. Tau max. How it occur? We know that tau equal to mu du over dy. So differentiating this equation, mu d over dy in bracket 1 upon 2 mu minus dp over dx and by minus y square. So now it will equal to take mu replaced. So mu upon 2 mu minus dp over dx and that is du over dy. So b minus 2y. So for maximum, putting value of where tau will be maximum. This is a value general equation of our tau. So when we take a y equal to 0, at y equal to 0, you will get tau maximum. Tau maximum equal to b upon 2 minus dp over dx. This is a maximum value of tau because you will get at y equal to 0 and y equal to minus b. Y equal to b at y equal to b also you get maximum value because both are at y equal to 0 you will find maximum value of tau, and at y equal to b, here putting y equal to b you get minus value. But magnitude of this tau shear stress will be same, b by 2 minus dp by dx. This is maximum value of the shear stress. You see here maximum value of shear stress you get at y equal to 0 or y equal to b. At y equal to b by 2, what will value? At tau equal to y equal to b by 2. Putting this at y equal to b by 2, it become b and b minus b equal to 0. So y equal to b by 2 you will calculate 0. So at center line shear stress is practically 0. How you see that at center line shear stress is going to be 0? Because here velocity is maximum and shear stress is 0. Here velocity is 0 and shear stress is maximum. This is a shear stress distribution. Now let us see what is we have already calculated maximum velocity u maximum we have calculated equal to b square upon 8 mu minus dp over dx. How we find average velocity? Because all engineering calculations are performed, you see that velocity is varying from y equal to 0 to y equal to b. So what will be average velocity between whole of the parallel plate, between two parallel plates, because it is varying. So for all engineering calculation, for calculation of head loss, for power required to maintain the flow, we require average velocity. So how we can find average velocity? Here we see that this is a u dy. Here we have taken u dy. See thickness dy. So what is discharge from this thickness? So we see that dq from this small strip of dy, how much discharge is taking place? So dq equal to u dy and per unit width along z direction, because z direction width is infinite. So we will take 1 unit, means we multiply it by 1. It becomes per unit width of the plate along the z direction. Depth of this along z direction is infinite. So dq equal to u dy, and so q equal to integrating from 0 to b, because we have to integrate from 0 to b, we get whole of discharge u dy. Putting value of u 0 to b 1 upon 2 mu minus dp by dx and by minus y square dy. So integrate this one. Integrating this one. So q equal to 1 upon 2 mu minus dp by dx. Integrating this equation from 0 to b, that is equal to b y square by 2 minus y cube by 3. Limit of integration is 0 to b. Simplifying this equation, take common 6. Simplifying this equation, we will get b cube upon 12 mu minus dp by dx. Simplify this integration, we will get Q, total discharge between two parallel plates. So here we have to find out average velocity. Please keep this one very consciously, that how we are taking different parameters. So how we calculate average velocity? So V average equal to discharge upon area. Discharge upon area, that is equal to B cube upon 12 mu minus dp by dx. So this is a discharge, and what will be area? Think about area. Area is we know B and into 1, because we see that what will be area? If it is a width, and area will be along the z direction, that we have taken per unit width, that is we take 1. So multiplied by 1, so B will be 1, B will be replaced, it becomes B square upon 12 mu minus dp by dx. So this is a average velocity, and what is the ratio between average velocity and maximum velocity? V average upon U maximum equal to, you get B square upon 12 mu minus dp by dx upon B square upon 8 mu minus dp by dx. Replace everything, b square mu, it will become 8 upon 12 equal to 2 by 3. This is a very important observation, that average velocity to maximum velocity for this distribution is equal to 2 by 3. V average upon V maximum equal to 2 by 3. This is very important observation. But in actual case, we have to find out what is a head loss in terms of the water column. What is a head loss in terms of the water column? So again we take average velocity, concept of average velocity. Already we have derived average velocity. This we already derived V average equal to B square upon 12 mu minus dp by dx. This is equation for average velocity. From this equation we can get minus dp by dx equal to 12 into mu V average upon B square, minus dp equal to 12 mu V average into dx upon B square. Now integrating again both sides, pressure P1 to P2 and dx from x1 to x2, because here suppose x1 and final length is x2. So integrating this one, minus dp P1 to 1 to 2 equal to 12 mu V average upon B square dx 1 to 2. So equation we get dp P1 minus P2 equal to 12 mu V average x2 minus x1 upon B square. This x2 minus x1 we can express in terms of the length of the pipe, length of the plate. Between 2 points x2 minus x1 we can define simply by length of the plate. So we can simply say P1 minus P2 equal to 12 mu V average into L upon B square. So we can also define this equation in terms of the pressure gradient. If you define pressure gradient terms, P1 minus P2 upon L, pressure difference per unit length between 2 points. Pressure difference per, because in some question it is given pressure difference per unit per meter. This is pressure difference per meter equal to 12 mu V average upon B square. But most of the time we have to find out head loss. That head loss we have to define in terms of the length of the water column. So again we write equation P1 minus P2 equal to 12 mu V average upon B square. So dividing P1 minus P2 by specific weight of the water, then pressure difference in terms of the loss of the head loss between 2 points, that is here length will be, again here we multiply by length L, so 12 mu V average L upon omega B square, WB square. Here W, small w is a specific weight, small w is a rho G, rho water. If there is a water, if there is another other fluid, we can take other fluid density. But this equation, this you can say in terms of the total head loss occurring because of the flow of the any fluid through the length L, that is equal to 12 mu V average L upon omega B square. This is most important relationship of Hagen-Poiseuille. This is not Hagen-Poiseuille because Hagen-Poiseuille is used for the circular plate, circular tube. Here you can find out head loss. Sometimes we have to define out power required. What is power required to maintain this flow? So power required to maintain this flow, you can use equation, because we know equation of power. Power required, we have calculated H, L. Total head loss in terms of the water column, if W is A, omega is A, actually for water omega is given 9810 Newton per meter if there is a water. If other fluid, then we have to modify it. Head loss, if you know head loss, then you can power required. Power required equal to omega QL upon 1000. Omega QL, here L means HL, L means HL, head loss. If you know head loss, then it is simple. Omega is a specific weight of the liquid, Q is a flow rate, meter cube per second, and dividing by 1000, then you get power kilowatt. This is all about discussion flow between two parallel plates. This is very simplified way of deriving equations. So this is important from the examination point of particularly in Indian engineering service examination and GATE examination, because questions are asked from mid of the, because sometimes question may be what is a relation between average velocity to maximum velocity, and what is how head loss depend upon what parameter average velocity. You simply take a V velocity, means average velocity. HL loss depend upon the length, proportional to length, and inversely proportional to square of the width between two plates. So these things you have, and proportional to viscosity, dynamic viscosity. All, if you know all these parameters, then you can easily solve questions. So next, in next discussion, we will discuss about Hagen-Poiseuille equation, derivation, laminar flow between laminar flow through pipe. That is also almost a similar derivation you will find. Only thing that you will find difference is that here is two parallel plates, and in the pipe it is a circular pipe. I think you will like and subscribe please, and share it to your friends, and have a nice day and make comment. Thank you very much.